Our speaker today is Professor Neal Iverson. He's actually a candidate for the Evans Family Chair that is available here. Professor Iverson got his bachelor's degree from Iowa State University in geology, and then his doctorate from the University of Minnesota, also in geology, where he stayed as a research associate, then a senior research associate in the Department of Geology and Geophysics, and then he moved to Iowa State University to the Department of Geology, Geological and Atmospheric Sciences, where he's risen from assistant to now full professor, and he was also department chairman from 2011 to 2014. He's a fellow of the Geological Society of America. Today he's going to talk to us about glacier sliding, creeping towards better constitutive rules. Thank you.
Thank you, Ian. And thanks to all of you for having me here. It's great to be able to give a presentation like this in a place that has such a strong tradition in doing research on ice and snow-related processes. Today I want to talk about a really important mechanism of glacier motion. And before I do that, I need to remember to acknowledge this guy. This is my former postdoc at Iowa State, Lucas Zoot, who now is a assistant professor at UW-Madison, and who's still a primary collaborator of mine, and who was responsible or who worked with me a lot in a lot of the experiments that I'll be talking about today. Glacier flow isn't a very typical fluid flow problem from an engineering perspective. One of the issues is, of course, the nonlinear rheology of ice, the fact that if we go down through this glacier, the effective viscosity of the ice is strictly speaking different at every given depth as the stress increases with depth. And this is something that glaciologists have dealt with successfully for a long time in glacier models. Although there's still a lot of disagreement about the details of this flow rule for ice. And I'll talk a little bit tomorrow about our work on this problem. But today I want to focus on this more troubling problem, and that is the fact that unlike most fluids, glaciers, when they move over their substrates, if their ice is at the pressure melting temperature, slip can occur down here, and this slip can account for most of glacier motion, particularly when glaciers are moving really fast. And a long-term priority in glaciology, going back to the 1950s, is to develop a constitutive rule for this motion where stress is linked to motion in some rational way that can be used in large-scale numerical models of glacier flow. There are a number of reasons this is an important problem. This is the most topical one at present, and that is that basal slip ultimately gives rise to fast glacier flow, and where glaciers terminate in the ocean, that fast glacier flow leads to a high flux of ice to the ocean, and that, of course, is a big contributor to sea level rise. And so the ice flux, as indicated by, say, an ice sheet model, ultimately depends on the sliding law that's chosen. This is quite of a generous word because it's really just a guess. It's not a law at all. And this is a guess that relates basal drag to sliding speed and effective pressure, which for the purposes of this talk is just the difference between the ice overburden pressure and the water pressure that exists at the beds of warm-based glaciers. If you look at the literature on the development of sliding laws or models, you get all kinds of different possibilities that come out. This is the drag on the vertical axis here. This is just the basal shear stress normalized with respect to the effective pressure N, and this is the sliding speed normalized in the same way. And you can see this great diversity of potential behavior that people have actually derived from various mathematical models. But if you look at numerical models of big ice sheets or parts of big ice sheets, it's always, or almost always, a Weertman sliding relationship that's applied, such that the drag increases monotonically with sliding speed. And this is a convenient thing to apply because it ultimately means there's a stabilizing influence at the bed. The faster the ice is sliding, the more drag there is to resist that sliding. However, a few big ice sheet modelers like Catherine Rees a few years ago looked at a pretty great diversity of sliding rules and found, unsurprisingly, that this was a really big unknown in efforts to model the dynamic contribution of ice sheets to sea level rise. And one of the reasons has to do with this very topical problem right now in glaciology, which is called the marine ice sheet instability. If we imagine an ice sheet like this that terminates in an ice shelf, true of certainly large portions of West Antarctica, for example, and then we warm up the ocean, as we are doing, of course, right now, and start melting the undersides of the ice shelf, the grounding line retreats back. And if this slope of the bed is in the opposite direction of the glacier surface slope, which doesn't show up terribly well up there, what will happen, of course, is the ice will thin as a result of this grounding line retreat. And the rate of ice flow across the grounding line ends up being very sensitive to that thickness. But the degree of sensitivity ultimately depends on the sliding law that's chosen at the bottom. In any case, if the ice flux across the grounding line becomes progressively larger as the grounding line retreats, that's a feedback that thins the ice sheet and ultimately leads to still more grounding line retreat. And that's at the heart of the instability. And the sliding rule really is important in trying to estimate the degree of instability that really results. And so getting the sliding rule right is a long-term priority in glaciology, but also has a lot of topicality right now in the context of this pretty important problem. From my perspective, in part as a glacial geomorphologist, though, it also has great relevance for other things. For example, arguably the most spectacular scenery on Earth is a consequence of slip at the bottoms of glaciers, because that's how glaciers erode bedrock. That's how we take river valleys that are relatively unimpressive and turn them into places like this along the coast of Norway, where we, a number of years ago, used to work beneath this glacier right here. It also results in some landforms that aren't quite as spectacular but are probably more mysterious, like these drumlins, these elongate hills. These happens to be some drumlins we studied several years ago out in front of this surge-type glacier called Mullajökull in central Iceland. If you want to build a mathematical model for how these form, you need some kind of a sliding rule, because that sliding shapes, to some extent, drumlins like these. And then an example closer to home. This is where I live in central Iowa, in Ames. This is a till upland adjacent to Ames, where we have these very conspicuous transverse ridges. The Des Moines lobe came across here about 17,000 years ago and molded this landscape. And the leading hypothesis for this is that the ice was in a state of surging. It was, as a result, the glacier was in a state of extension all the way out to its margin. That led to periodically spaced crevasses on the glacier's surface that extended to the bed, and soft, wet till squeezed up into those crevasses. Again, if we want to build a mathematical model of this, we need some kind of constitutive rule that describes that surge-like behavior, in this case where the glacier was sitting on a sediment bed. So I want to talk a little bit about the different kinds of bed conditions. This is the glaciological shorthand that's used. Often glaciers, particularly in alpine regions, will rest on rock, irregular rock. That's called a hard bed. And sometimes glaciers are resting on some sort of water-saturated sediment, which is most commonly till. Till is just poorly sorted sediment that melts out directly from glacier ice. Here's the usual assumption that's made in modeling slip, that we have viscous or viscoplastic slip resistance such that basal drag increases with slip velocity. This is the Weertman sliding rule that I mentioned earlier. The fundamental point of my talk today is that we have lots of experimental results that indicate that this can be a really poor assumption, and that this probably underestimates the contribution of sliding in lots of cases. So let me expand on this a little bit. First, with some more background on what Weertman really talked about way back when in 1957. What he considered was temperate ice at its melting temperature, sitting on a regular rock. He considered something a bit more idealized than this, but the physics are comparable here. If we take the ice and put it on the rock, there's a thin water film that develops between the ice and the rock. It's anywhere from maybe a micron to 100 microns thick. And what this does is something really important. It takes the shear traction locally on the bed and reduces it to essentially zero. And that means the drag associated with slip over the bed is purely a consequence of form drag around these bumps. So pressure distributions develop around the bumps that really hold the ice back, the downslope component of the glacier wedge. Ice around large bumps tends to move in response to these stress gradients due to enhanced creep. And around small bumps, by small I mean less than, say, maybe a few decimeters in wavelength, there is this neat process called regulation where melting occurs on the upstream side. The water flows to the downstream side where the pressure is less. It refreezes. Latent heat is liberated, which moves as sensible heat back through the bump and melts more ice. And this is a result of the fact, fundamentally, that when pressure is applied to ice at its melting temperature, its temperature goes down. So this is the cold side of the bump. Okay, the key element here, though, is that ice is in contact everywhere with the bed. And at about that same time, there was a contemporary of Weertman's named Louis Le Boutry, who was kind of a cranky glaciologist from France, who, if you read his papers today, there's all kinds of very sharp statements in them you don't read in modern papers today. They're quite entertaining to read for that reason. When ice slips across an irregular surface like this, what Le Boutry realized, which is absolutely true, is that ice will often separate from the lee side of the bump because it's flowing faster away from the lee side of the bump than the pressure in the ice can force the ice by creep back towards that lee surface. This creep downward is resisted further by the fact that water pressures can be quite high at glacier beds, depending upon the nature of how these cavities are connected and how much water is pouring into the glacier. And that resists creep downward and keeps the cavity large as well. My point here is that in this case, the drag relationship is very, very different. This is the Weertman-style drag relationship. Drag is a function of sliding speed. It rolls over due to the nonlinearity of the ice rheology. Ice is getting softer at higher strain rates and higher sliding speeds. But the Le Boutry relationship is very different. Drag increases at low sliding speeds, and then at some steady state sliding speed, a threshold drag is reached. And at still higher sliding speeds, the drag actually goes down. This is what a fault mechanicist might call velocity weakening or rate weakening. And it's something that no one would have thought a glacier could do for many years. And we have pretty good evidence that this actually happens beneath glaciers. But my point now is the fact that this has really should really have a profound influence on glacier flow, for the simple reason that basically the bed is getting slipperier the faster the glacier slides. And that means that driving stress of the glacier, it's the downslope component of its weight, has to be supported somewhere else. So stresses are going to load up elsewhere, either on the bed where this isn't happening, or maybe on the sides, or maybe on an ice shelf. And that's going to cause faster glacier flow than you would get in the absence of a sliding rule like this. So there were subsequent theoreticians like Andrew Fowler and Christian Schoof more recently who've demonstrated this same relationship for more complicated bed geometries. But no one seemed to be very interested in actually testing whether this actually happens or not. And so I built a device that I'll talk to you about in a minute. But I see here that I also want to describe to you why this happens, why this decrease occurs. And it has to do with cavities. At low sliding speeds, it's like the Weertman situation, complete ice bed contact. At higher sliding speeds, a cavity starts to form. And as it gets bigger, the drag continues to go up until the reattachment point of the ice reaches the inflection point on the bump downstream. Then further increases in speed cause the cavity to climb still higher up the bump. And you can see the adverse slope on the bump now is getting progressively smaller. And that ultimately is what's causing this rate weakening behavior at higher sliding speeds. So how are we going to test this? Well, how many years ago now? 12 years ago or so, I got an MRI grant funded to build this device, which sits in a walk-in freezer in my lab. It's about 3 meters high and about 2 meters wide. That is the loading frame. And the important part is in here. This is where we build up an ice ring, which is about 9/10 of a meter in outside diameter, 50 centimeters in inside diameter, and about 1/4 of a meter tall. The ice chamber that the ice resides in is surrounded by a fluid that is circulated through this green tub with an external circulator, which keeps that ethylene glycol water mixture to a particular temperature with a precision of about 1/100th of a degree C. And so with this fluid, we can keep the ice at the pressure melting temperature without melting it too quickly, because we need this ice to persist for several months, in some cases, during these experiments. A vertical stress is applied with this hydraulic ram at the bottom. This ram keeps the stress constant, even though the system sometimes wants to dilate or contract. And importantly, this platen grips the upper surface of the ice with some teeth and can rotate at either a constant torque or a constant speed, and that drags this ice ring across some sort of artificial glacier bed, in this case a stepped rigid bed. So that's how it works, and this is what it looks like. This is the freezer, and this is the green tub that has the temperature-regulated fluid in it. This is the upper platen that rotates and grips the upper ice. You can't see the ice chamber here. This is a motor that is one of 2 such motors that are geared down by a factor of about 2 million to drive this plate. That's why these motors can be so small. These are just some leads to various sensors. We put lots of thermistors in the walls of the device. Thermistors calibrated to the nearest 100th of a degree so we can keep precise track of what the temperature is in this experiment. Because even if it falls 1/10 of a degree below the pressure melting temperature, things can change pretty radically. And then this is a Weertman for scale. This is the ice ring that we just shown schematically, and this is the first bed that Luke and I worked with, which is a sinusoidal bed that is torqued a little bit to accommodate this radial geometry. We used a sinusoid because theoreticians subsequent to Weertman had used a sinusoid. Leboutre was one of the first to actually consider a sinusoid. We also made the bed not out of rock, but we made it out of a high-density plastic called Delrin to inhibit redulation. The thermal conductivity of this stuff is something like 10 times less than that of rock. And what this means is we can scale up these results better to the larger scales of bumps that more recent sliding theories have tended to focus on, work by people like Christian Schoof. Okay, this is what the ice ring looks like before we put that upper platen down onto it. I should mention a little bit how we build the ice. We take deionized water, we freeze it, we crush it into snow, we put it in thin layers in the bottom of the ice chamber, and then we flood those layers with deionized water. So we generate, at the beginning of an experiment, crystals that are a couple of millimeters on average in diameter and with relatively random orientations. We also put strings of beads in the ice, vertical columns, and we can, with both a video or 2 video cameras that look through the walls, we can track their relative motion, and we can look at their relative motion at the end of the experiment when we pull this thing out of the ice chamber as well. We want to look at the distribution of strain in the ice. This is a time series of the sort we gather in these experiments with drag on the vertical axis. Shear stresses here between what are a relatively steady shear stress here of about 145 kPa. We're running at a controlled sliding speed, and then here we increase the sliding speed abruptly. And just as in fault mechanics experiments, we get this very pronounced direct effect where the stress goes up, and then it falls off over about a 1-week period and settles in eventually again to a steady state. This is the period of cavity growth, where that cavity is extending to its new steady state size. And that takes a while, an amount of time proportional to the sliding speed. These are what the cavities looked like in this experiment, bearing in mind here that the amplitude of the bed here has been greatly exaggerated. These are cavity roofs attained at different sliding speeds. You can see that by the time we got to a sliding speed of about 300 meters per year, the ice was just skimming across the tops of the bumps. And I think everyone can appreciate that drag should be pretty low in this situation. The other thing I should mention about these experiments is water is allowed to drain from the bed to atmospheric pressure. And so we apply a total stress, in this case 500 kPa, that we think is a reasonable number for the effective stress in a real glacier. The other thing I want to point out is note this speed of about 7 meters per year here when the ice reattachment point is at approximately the inflection point of the bump downstream. Now I want to show you the drag-velocity relationship that took us a couple years of experiments to produce. These open diamonds are for stress-controlled tests that we did at these very low velocities. The closed, darker diamonds are for speed-controlled tests. And you can see that just as Labutri predicted, there was this peak in stress at just about the right sliding speed relative to where that ice reattached with the bed. And then there was this wide range of sliding speed where there was rate weakening behavior. This line is not a fit to the data. This line is combining Labutri's theory with Barclay-Cam's theory of cavity formation, the Lee of sinusoidal bumps. And I want to point out there are no adjustable parameters in putting this in this line through here. And so this seems to work out quite well. So this potentially has big consequences if it really happens in nature. It would mean that, again, the glacier bed is getting slipperier by quite a bit the faster the ice slides. Now, if only this bed were supporting the glacier, that would mean that the glacier would accelerate into some kind of destructive debris avalanche, and that almost never happens. So what's really going to happen in this situation is stresses are going to get shifted elsewhere, and that's going to give rise to a higher strain rate elsewhere and a higher flow velocity overall. So another question that some of you might be asking, a really good question, is this ice, which we just built in the lab here, is it behaving like real glacier ice? And I would argue that early on it's not, but that for most of these experiments it is. And that's all about total strain. This is the ice ring the way it looks after we've pulled it out after an experiment. This is where that upper platen gripped the ice. And this is an initial vertical column of beads that has been deflected very markedly here. And you can show here that the shear strains were greater than about 25 in this lowest third of the ice ring. You can also see how the air in the ice has been completely expelled down here, associated with recrystallization. Well, what about the structure of the ice? If we do what glaciologists have been doing for a really long time and look at this ice under crossed polars, you see a lot of these grains are extinct. And what that's telling us is that the c-axis of that hexagonal ice crystal is plotting more or less vertically. This is a lower hemisphere stereo plot. And what that in turn is telling us is that when recrystallization occurs, those easy glide planes are forming subparallel to the overall shear plane. Note the crystal size of about, a lot of these are about 10 millimeters. This is a lot of grain growth that occurs in these experiments as well. I remember the initial grains are about 1 to 2 millimeters. And this is just for comparison. This is some ice sampled from near the bed of the Barnes ice cap by my former advisor, Roger Hook, a long time ago in the 1970s. So I think we can. I think this is, in fact, at least comparable in this regard to real glacier ice. There are other things that are very different. There's no debris in this ice, for example, which is perhaps an important element of this problem as well, as I'll describe in a little bit. Okay, I'm going to switch gears now and move to this other bed condition where we have temperate ice, that is ice at the melting temperature, sitting not on rock, but on water-saturated till. This is where this water-saturated till is thought to activate really fast glacier flow. And this is the idea as to what's going on here. We get a velocity profile that looks like this, such that the ice is moving mainly by just riding piggyback on that deforming sediment layer, and that layer is deforming across most of its thickness. That's the idea that was promulgated a lot in the 1980s and 90s as well. And this is another assumption that was made commonly, that till behaves as a viscous or viscoplastic fluid in this situation. And these are just some of the studies where this idea was used as a starting point for modeling efforts. And I want to argue now that this is wrong. I was interested in studying this a long time ago as a postdoc in the 90s, and as a result, I built this different ring shear device, which sits in the warm climate outside my cold room. And the way this, well, first of all, this is designed. This is something basically a design I stole from some geotechnical engineers, Bishop et al. At Imperial College, who had designed a ring shear device quite a bit like this 20 years earlier. And I just increased the scale a little bit in designing this thing. This is the sample chamber where the till sits. And this is about 60 centimeters from here over to here. We don't use an intact till sample. That would be very difficult to collect. We put a disturbed till sample in here. We saturate it with water, and that water is connected to this interior reservoir through some channels that you can't see here. And that reservoir is kept at atmospheric pressure. So this is a so-called drained experiment in the vernacular of geotechnical engineering. This upper plate that you see here fits down on top of the till over this area. And this lever arm with a dead weight exerts a downward stress on the sediment. This bottom part rotates, and the upper plate wants to rotate with the bottom but can't because it presses on two diametrically opposed load cells which measure the shearing resistance. And then we correct that shearing resistance a little with another measurement of shear stress on the upper walls that needs to be taken into account. And that's measured with this torque sensor up here. Well, what did we do in these experiments? We simply sheared the till at different rates and looked at the shearing resistance. And we chose a couple of different tills that were readily available. What I'm going to do now is show you results not only from our experiments, but from some other experiments using slightly different devices. And what I've done is not shown the data here. I've just shown the fits to the data. On the vertical axis is the steady-state strength of the till attained at high strains. That's called the till ultimate strength. And we've normalized it with respect to the effective pressure, which in these drained experiments is equal to the total downward stress on the till. So this is really a friction coefficient, a steady-state friction coefficient on this axis. And then we have strain rate on the horizontal axis. And what you can see is there's just no compelling dependence here that's at all serious with respect to shear strain rate. And that's not indicative, then, of some sort of fluid rheology. This is, in fact, a Coulomb material, which really should have been the starting point for models. And this is one of those cases where geoscientists weren't tuned in well enough to the engineering literature on this subject. What does control the till ultimate strength? Well, the effective pressure does. The harder we press downward on this till, the stronger it gets. Not a very difficult concept to appreciate. Now, I will say that some of these results indicate mild rate weakening behavior. And that's important because this is one of the criteria for stick-slip behavior at glacier beds, which has been observed and something I'll talk about a little bit tomorrow. What about the kinematics? Are the kinematics of this model right? And I would argue that measurements we and others have made through boreholes in tills beneath glaciers suggest that this really isn't the right kinematics either. That in fact, most measurements indicate that strain is focused in the bed right up near the glacier sole. I haven't listed this study, but this is what Herman Engelhard and Barclay Kam measured beneath Willen's ice stream in Antarctica a long time ago as well. So I really should list that here as well. So how does this happen? Why might strain be focused near the glacier sole? And what I have argued in a few papers is that it happens by plowing. This is something we in Iowa understand very well. In this case, we have clasts at the ice-till interface that poke partway up into the ice and poke partway down into the till. And if you jack up the pore water pressure in this till, it gets sufficiently weak so that the drag that the ice exerts on a clast like this basically causes this clast to plow through the substrate. And we can see this actually in the geologic record. Not very often, because these bedding planes in tills are not often well preserved. In this case, this is a bedding plane from about 300,000 years ago in Illinois, where the till substrate has been turned into a rock, effectively, through calcite precipitation. Ice slipped from left to right here. This clast was dragged along. It formed a trough here. It formed a prow here. And you can see where ice slid around this clast by looking at these scratches, where debris in the ice scratched the larger clast. So I, for a long time, wanted to test this sort of model for what's going on at the ice-till interface. And once we had this device that I talked about earlier, we were able to do this. And again, this is work with Lucas Zoot. What we did is use this same device, only we took out the rigid bed and replaced it with till. In one experiment, in one set of experiments, we sieved out all the largest grains, so we just had grains smaller than 2 millimeters. And then in another set of experiments, we added back to the ice-till interface some larger clasts that were, I think this is a radius actually, that were a little over a centimeter in diameter. And then we slid the ice that was at its pressure melting temperature across this till bed at a range of speeds. We again kept the ice, as I said, close to the melting point. And then we let water drain from the bed so that we didn't develop a deficit or an excess in pore pressure here, and we kept the pore pressure as a result very close to atmospheric pressure. That simplifies this kind of experiment. And then we tried to look at both the kinematics and the sliding law that results from this. This is an effort just to see how the bed was deforming. We've got an initially vertical column of beads in the till. This is after an experiment. Here's where the ice ring was. Most of it's been chipped away. You can see how most of the motion occurred up here. The next bead higher is way off the picture here. So motion up near the top of the till bed. This is showing that same thing, where we have the fraction of total slip on this axis and the bead displacements on this axis. And much of the displacement we simply couldn't resolve due to the size of the beads. So moving on now to what the slip rule might be in this case, I want to remind you of the Weertman-like behavior, this viscous behavior. Now, to be fair, some people who have used this kind of nonlinear viscous behavior for till have acknowledged that there is a threshold shear stress below which there is only elastic deformation. And this is what might be thought of as the other end member, just Coulomb behavior, where once a particular shear stress is reached, the sliding speed at that point is basically indeterminate. So this is the result from an experiment with clasts. You can see, and let me tell you what's plotted here. This is the shear stress that's measured in the experiment, normalized with respect to the strength of the till, measured in other experiments, which are called direct shear experiments, where we're just shearing the till and getting a friction coefficient for the till. And you can see that basically over much of this range, the resistance to shear is simply equal to the Coulomb strength of the till. It isn't changing as a function of sliding speed, but you can see at the low end, we're getting some rate strengthening. Well, one of the things we can do is use a model of mine that predicts the sliding speed at which a given distribution of clasts should start plowing for a given effective stress on the till bed. This is a model that is based on what are called cone penetration tests that geotechnical engineers do. They'll take a cone and they'll press it down through a geologic substrate at a constant speed, and they'll measure the force required to do that. And so it's easy to adapt a theory like that to this plowing problem, and that's all I really did here. And this is the speed that the model indicates plowing should ensue at. And you can see this is when we start following a standard Coulomb model for the till. If we go to the other experiments where we sieved out the clasts, you can see that we get the same thing, only there's a much broader range over which we tend to get the this rate strengthening behavior, albeit we don't have as much data in here as we would like. What does this mean? Well, what this means is that when we have clasts at the ice-bed interface, it takes a smaller sliding velocity to exert enough drag on the bed surface to get that bed deforming. And when we have no clasts at the ice-bed interface, it simply requires a higher sliding speed to get to that state. A simple-minded thing to do is to try to just fit a power law to data like these. First of all, the fits aren't at all good. And second of all, the power law exponents are very large. And when you have to invoke a power law exponent of this size, it probably makes sense to step back and ask, is the power law the right sort of thing to use here? And so what we favor is an explanation like this, which is, to some extent, I've already explained now. We have rate strengthening behavior up to some transitional slip speed, at which point the drag on, in this case, clasts at the bed surface is enough to get them plowing so that we're operating here at this Coulomb strength of the till bed. And then when we take away those clasts, we have the same kind of behavior. It simply requires a higher sliding speed to get to the point where the shear stress on the bed surface is enough to deform the bed. And this would be the relevant kinematics, where in this case we're getting just sliding of ice over this field. We're sliding ice across the till bed. And then over this part of the range of parameter space, we're just getting deformation, but focused right up near the bed surface. So a simple way to think about this is to simply argue that the basal shear stress here is the smaller of either the drag associated with Weertman slip at some velocity u sub b, or the Coulomb strength of the till, which is given by the effective stress here multiplied by this friction coefficient, which for soils is often written in terms of this friction angle phi. And then the transition speed was simply then given by this model. So this is the constitutive rule we would argue is relevant to ice sitting on a soft bed. Bearing in mind that just about everybody who's done this has treated the till like a viscous material. And that's not universally true, but it's usually been true. Okay, how much time do I have? I don't want to go long here. I want to tell you where I'm going with this because, as was pointed out, this is a job interview, and I'd like to be telling you what we're doing now and what we will be doing in the relatively near future, I hope. We want to add realism to these sliding rules. And ultimately, we want to know what the full range of possible sliding behavior is. Because if we don't know what that range is, we don't really know the uncertainty of these predictions of sea level rise over the next century. So we want to get a better handle on that by adding realism first to our experiments. One of the things we're doing right now, an experiment is running like this as I speak to you now. We have ice built in the way I described earlier in this same device, only now that ice is being slid across a smooth rock bed. And in the ice, we put debris particles, because real glaciers, down at their bottoms in particular, have debris particles in them that have been produced by erosion of the bed. And we want to know how much friction do we generate with these debris particles. Now, we know when we slide clean ice across the bed, when the ice is at the melting temperature, we get friction coefficients which are just really, really small, 0.002. That's the friction coefficient when we have ice at its melting temperature across this polished granite slab. What do the rocks do in the ice? Well, that should lead to a local shear traction that we don't get otherwise. So what's going to control that shear traction? Well, our first inclination here is, well, it must be the effective normal stress. The harder we push down on this ice, certainly the friction will go up at the bottom. But the first experiments that we've done on this, beginning last fall, show that that's not true at all. When we increase the total vertical stress on this ice, the rock friction doesn't increase at all. And the reason we think is that we develop, first of all, cavities beneath these particles that are filled with water. And the water, although it's allowed to drain off the edges of this bed, ultimately the water pressure in those cavities ends up being commensurate with the ice overburden pressure. And so when we increase the total normal stress on the ice, the water pressure increases as well. And that reflects the need to evacuate this water produced by melting around these particles out along the bed surface. So the hydraulic gradient increases, and that basically nullifies the effect of the increase in total stress. What does this depend on? It depends on something Bernard Hollay hypothesized many years ago in the late 70s when he was studying glacial abrasion. It depends on the ice bed convergence rate. Ice at the melting temperature as it slides across a bed will melt at the bottom a little bit, so a component of its velocity is towards the bed. In addition, when ice flows over a bump by enhanced creep, there's stretching of that ice parallel to the bump surface, and that pushes the ice towards the bed as well. What does that do? That ice motion around these clasts exerts a viscous drag on the clasts and presses them against the bed. And that is what we're learning is responsible for debris bed friction. And now that we're developing empirical rules for this, we can start to think about adding this in to a more realistic model of glacier sliding. That more realistic model has to have in it realistic bed geometries. Although theoreticians would really like to have sinusoidal glacier beds, they don't exist, okay? And the reason they don't exist largely has to do with geology. In this case, we have a ground-based LiDAR system out in front of a receding glacier in the Canadian Rockies. This is a couple summers ago. This is Luke and I in here resting, as we did a lot in this field work. We had a UNAVCO helper with us who largely ran this ground-based LiDAR system. And we got really good high-quality digital elevation models of this glacier forefield. It's stepped like this because these are sedimentary rocks that are bedded in this way, and so the glacier erodes off the rock along these bedding planes. So we have some glacier beds that look like this, and then last summer in August, we went to the Alps and visited 10 more glacier forefields that have been recently exposed by glacier retreat. And we used a drone-based camera to ultimately do structure for motion analysis of the photogrammetry to get, again, pretty high-quality DEMs of these proglacial surfaces. Here's another example. In this case, it's metamorphic bedrock from a different part of the Alps than this part. These are the Bernese Alps. And once we have these realistic glacier beds, real glacier beds, we want to then reduce them to what we might call representative elementary areas. We want to do the spatial statistics on these very large areas that we've mapped out, and ultimately, with those statistical parameters, identify small windows of the glacier bed that are representative morphologically to the larger bed area. And these are some of the things we do. 2D discrete Fourier transforms to look at dominant wavelengths and their orientations relative to flow. We look at the convexity of Stoss slopes, bump asymmetry, and so forth. And then, this is all leading up to this modeling. This is being done by my postdoc, Christian Hellenau. And he has a lot of experience with using this particular code. It's a fluid dynamics code developed initially to not study ice, but it's people like Olivier Gagliardini at Grenoble have worked very hard on adapting this code so it's a bit more user-friendly for ice. And what we want to do is, I see that there's some, I guess there's some lines missing in here. It doesn't really matter. This is a block of ice sitting on one of these representative elementary areas. These are the boundary conditions in this modeling. These are the governing equations, which is just Stokes' flow with a nonlinear ice rheology. This is the viscosity parameter in the flow law, B. We basically push this ice block across these rough surfaces that we've mapped, and we calculate the basal drag at values of at various values of this ratio between sliding speed and effective pressure at the bed N. The hard part of this problem is getting these cavities right at the bed. We need to get ice bed separation into this problem because that's what gives rise to the rate weakening friction in experiments. And the problem is we don't know where these cavity roofs are a priori. This is a free surface, and so we need to iterate with the model until we get velocity vectors along the cavity roofs that are parallel to the cavity roofs. And that tells us we've reached a steady state condition, and then can go back and do the integration across the bed that's necessary to get the drag. So this is what Christian is just starting on right now. He's done some idealized bed geometries to see how this model is working. And it works quite well, but there are some major challenges moving to these more realistic bumps that have to do with stress singularities and whatnot. And he's still working on that. The last thing I want to talk about here, and I'm almost finished, is our ultimate goal, which is to, once we get those drag relationships worked out for clean ice, we then want to add debris back into these investigations of the sliding rule. We can start out by getting a steady state flow in steady state cavity size. We can then add debris into the model, and from the flow field, from those convergence rates, and using our experimental data, we can then introduce some local shear tractions due to debris, and we can recalculate the drag. The problem is that isn't, strictly speaking, correct, because once we put the debris in, that's going to affect the flow field. And so we have to iterate between the flow field and the ice and these two orthogonal shear tractions on the bed until they're consistent with one another. And then we have a truly steady-state solution. And then we can go through and, again, look at various values of drag as a function of sliding speed. The last thing we would like to do is recognize the following, that some beds of glaciers erode so easily that debris is produced faster than it can be transported away. And that's when you start to develop a soft bed. And that soft bed develops first in the lee of bumps where the pressure is the lowest. And we can add till into this model, too, and say, well, let's assume the Coulomb strength is operative here at this interface. And we can go through a similar iterative procedure that we used in this case. So, to finish up now, what do our experiments indicate? One is that rate weakening drag can indeed occur, at least on some hard beds. And we're still exploring whether this really makes sense for more realistic hard beds. We've got to implement this modeling before we can really make a conclusive statement. And that's something that I would be working on here, of course. Rate strengthening is possible on soft beds, which kind of surprised us. But the fact is, when glaciers move on soft beds, they tend to move quite rapidly. And so we are likely to exist over that, beneath real glaciers, in that field of velocity where Coulomb friction is probably operative. So I think that's still a good idealization for soft-bedded glaciers. And then finally, and most importantly, I think what this work shows is that Weertman, that is rate-strengthening sliding rules, used in nearly all ice sheet models, very likely underestimate sliding speed. And that in turn means that we're likely underestimating ice fluxes to the oceans and potential sea level rise. So with that, I'll thank you for listening so intently, and I will, I guess, open it up for questions.